Well, hello there. Today we're going to go over Lab 2, the flowcharts and process mapping. A simple flowchart, you start with something, you do something, then you end. This is our first of our total quality tools that we're going to look at this quarter. We're going to look at the engine of Lean Six Sigma is the DMAIC methodology. It's define, measure, analyze, improve, and control. We're going to see this throughout the whole quarter here. The DMAIC is a methodology that we use in order to see things in a way that we can improve or insert opportunities. It's a linear process. It all starts when we define the problem, we measure the effects of the problem, we analyze for root causes, we implement and test improvement efforts, and then we develop systems to control the process so the future problems will not occur. So after the project is done, we're in the control phase. Then we go back to define, which is the continual circle of improvement, otherwise known as Kaizen. We're always constantly improving and looking at our process to weed out defects and problems. In addition to the DMAIC, we're going to be looking at the A3. The A3 is a methodology that's used extensively in high-level service, like healthcare, tech, and logistics, and also in manufacturing. It uses the bones of the DMAIC. The A3 views the problem or an opportunity as it exists now and how it could exist if improved or opportunities are acted upon. Like the DMAIC, there are robust efforts to identify root causes of problems, and the A3 uses the scientific method in using to test hypotheses for improvements in opportunity efforts. So there's 9 phases in here. There's 5 phases in the DMAIC. The DMAIC and the A3 are woven together, as we'll see here. In the define phase of the DMAIC, we have the 3 phases for the A3. Define the problem, understand the current state, visualize the ideal state. In the measure phase, we have the root cause analysis. Analyze phase, we have the develop solution hypothesis. In the improve phase, we have the conduct experiments, evaluating results, and implementing the best ideas. And then in the control phase, you're institutionalizing the change. So you'll see that we use both the DMAIC and the A3 throughout this quarter in order to define and also to improve or create opportunities. The quality tools that we're going to be going through in this quarter are the flowcharts, which we'll do today, the fishbone YY, the check sheets, the Pareto charts, the control charts, the process capability studies, and the scatter plots. Today, we are going through the flowchart. So the flowchart, we use it in the define and the control phases. We could use it in the measure, analyze phase too, or improve phase, but right now we're looking at doing it in the define and control phase. And then specifically in define phase, we're looking at to help define the problem, understand how the process looks now, and then visualizing what we like it to look like. Sans problem, without the problem. And then in the control phase, we use it to institutionalize the change in order to create an SOP, a standard operating procedure, so that the problems will never occur again. They're wiped out of the process. So in this particular way that we're going to use the flowcharts in Lean Six Sigma, we're going to use them for 3 ways. Number 1, defines the problem, help defines the problem, understanding the current state, how the process looks now, how we would like it to look, and then how the process is engineered so that anybody can look at that flowchart and say, okay, this is how we do that process correctly. So 3 different ways. Very cool. It's graphic. The workflow diagram in a flowchart it's a graphic representation. It shows the flow of work in a process from inputs to outputs, all its related sub-processes, all the activities, all the information, all the dependencies, and the sequence of decisions and activities that occur in the process. We're going to be using two terminators in our particular uh, process in this lab. We do not want to have more than one terminator or more than two terminators. We want to have a start and we want to have a stop. So the this particular shape is a rectangle with kind of a curved ends here. You only use it two ways. You start the process and then you stop the process. It's like a go stop sign. So there's only two ways. There's no yellow. There's no other colors. It's just start, stop. Um, and what's cool about the flowcharts is that these are all internationally known symbols. So we can go anywhere in the world, show a flowchart, and everybody will be able to realize or decipher what those shapes mean. The process node, it means you're just doing something, right? You're doing something. So it's just a rectangle. Decision nodes, they're diamond shapes. They're a binary output, so there's either yes, no, pass, or fail. The document nodes, these are kind of like the wavy line there. This could be any kind of a PDF, any kind of a document that's spit out of the process, for your invoice, receipt, job ticket, or whatever. Here is where we want to look at these non-value added potential nodes. Obviously, the delay node is obviously always going to be non-value added. Um, it's removing energy from the process. Anytime we have to do a manual operation, that's something we should look at. You can see these are all grayed out. Again, we want to make sure that these non-value added nodes that are removing energy from the process are potentially or could be non-value added are identified through a shade. Now, obviously, not all decision nodes are going to be non-value added. Some decision nodes will have value on there, but we just have to look at anytime we see this particular shape, we got to ask ourselves, are they adding value? And how I like to define non-value added is if the customer knew about what was going on in your process, would they be willing to pay for it? If they wouldn't be willing to pay for it, then that is a potential indicator of a non-value added. Some other nodes you could look at, you've probably seen these in other classes, the predefined node, a predefined process. There's more stuff going on in that particular process node than just one or two processes. It's pretty complicated. And then we have disk, which is any kind of a storage device, display, monitors and such. And then connectors to say, look, we're going to connect this flowchart to another flowchart instead of having a terminator node. Flow lines, you need a flow from one node to another. Every node has to be connected. To think about flowcharts as being an upstream and a downstream in a river. So the flowchart should flow naturally in one direction, or they can traverse like a river, kind of like a little snake, but they have a logical flow. And we should always try to, in the ideal phase, engineer our processes so any type of error detection or problems would be identified at the start of the flowchart rather than the bottom. So just think if you're like floating on the Sacramento River, you forgot your keys, 15 miles down the river, that would be a much greater hassle for you to get your keys rather than if you just found them right there at the start of the river rafting trip, right after you got off the boat, right when you got on the boat. So you could think about that. Just when we're engineering our processes, any type of a potential detection for a problem, we want to have that on the upstream. Here's a simple workflow: start, do something, and then stop. This is a workflow we have for you receive the pages. It starts the process, submit pages to hot folder, goes to the pre-flight, There's a decision node, pass or pre-flat, yes or no. If yes, it goes to the logical conclusion of pages imposed, sent to RIP, and then you have the output, which is a valid process. However, if it says no, it does not pass pre-flight, this is where I was telling you about we can't have more than one, two, three. We can't have more than two terminator nodes. Here's a terminator node here. In reality, would we just stop if the pages are rejected? Oh well. No, this would have to be reassigned as a delay node, and then this would be going over to another process, perhaps another non-value added. Why did the decision node? Why did the problems? Why were they rejected? Was it our problem or was it a customer's problem? Here's a key point when we're doing these flow charts. We got to ask ourselves, is things adding value? So let's just say the customer, we gave them a proof, right? In a process node, we do a proof, and then we give them the proof, and then they approve it or not approve it. If they approve it, great, goes to the next process. If they don't approve it, we need to add another decision node saying, well, why didn't they approve it? Did they not approve it because we missed something as a designer? Or say like they told us to insert a photo and we missed the photo. Um, if that's the case, then that would go to a non-value added delay that we have to fix the problem, and then it goes back into the process. You can see, so that would be a delay, that'd be non-value added. However, if the customer did change something, customer's always right. They wanted to swap this photo other than that photo. Then that would be a value added process. We fixed the files. So that's the thing we got to think about. It's like, well, what's got to ask yourselves? Is this valid value? Or is this non-added value? If anything the customer adds or changes, that's adding value because we're responding to the needs of the customer. Again, Lean Six Sigma is very customer centric. However, if our process failed and we have to rework or do something over again, then that's non-value added. A swim lane is a really cool way to to overlay a process map in order to differentiate, say, different parts of the process, how like different customer levels or different process, um, you know, areas of process like in manufacturing, design, print, bindery, or app development. People who are doing the wireframes, all that sort of thing. So in this case, you see we have a customer, we have a sales, we have an invoicing, and we have a warehousing. Those are all different aspects of the process, elements of the process. And then here we have that overlaid over our process map. So all of the customer or the order generation and process payment, the sales, complete the order, credit problem addressed. Is it okay? So you can see that we know exactly where those areas fall in the process and what elements they belong to. And then we have also original process and we have an ideal process. We want to map the workflow from the beginning, warts and all. We want to identify anything that's causing problems, or we know even if it's blaringly obvious, we could fix that. We want to make sure we put the map, the workflow, warts and all. We want to find out where our rework loops are. Where are those, constant cycles going back and forth between decision nodes and process nodes and delays and all that. That would be an area for us to look at. Redundancy. So say if we were doing something up here upstream and then we were doing something similar downstream, can we get rid of the downstream activities and just move it up here? Is there a better way to engineer that in order to get that process, get rid of those redundancies? Find the paper. Anytime we see a paper node or a document node, it's something to think about. It's like, well, is there a way that we can automate? Is there a way that we can get rid of that document? Key point here is that whenever we identify a non-value added node, either be it a delay, a decision, a manual operation, or a document, we want to shade it. We want to differentiate it from the other nodes to say, hey, this is non-value added. Here's an example. So this is a current state I did of a process. It was our invoicing process. So there was two different invoicing systems in this process. It took actual physical transit time, a waste from my company, my portion of my place where I work, to the other process, the business services. It took 2 days to travel. There was 5 documents per invoice. It took them 360 minutes to process the invoices again, so it was a duplicitous process. And then it took 45 days from the date of the invoice to when the customer paid the invoice. Incredible amount of waste. It was causing a heck of a lot of problems. So here's what I did. So I saw this, I knew there's a problem. It's good to map. I could show this to people and say, hey, look, we got to fix things. And then we do brainstorming. We do all the other tools that we're going to talk about, the fishbone why, find that root cause, and then we change something. And then we go to the next. So I did something. And then after I've done my hypothesis, I tested it out. After a couple of weeks of testing the new process, and then I could come up with a new ideal state flowchart that this is where we want it to be. So the ideal is there's only one system. It's archived on one particular process. I can send the invoice 2 ways myself. Here is a delay and a non-value added that was inside the system, even on the ideal state, because we couldn't take credit cards at the time. However, since that time, since this was made, we have been able to take credit cards, so we have eliminated all of these existing delays. So what usually take 45 days now takes 12 days. So you can see that's an incredible improvement. Here's another flowchart I did, and here I use swim lanes to identify the unintentional and intentional friction, which we'll go over in a minute. And anything that's removing energy from the process is called friction. And then also I have just like you see, like the heat maps of the nation where it's really hot and cool. You can see I have a heat map for the level of non-value added. So obviously the darker, those are the areas we want to address first, and then the lighter ones potentially could still exist in the process. However, it's something to think about for further improvement areas. So very cool. So you can, that's not, for us as graphic designers and graphic majors, you can see we can have really good impact on the organization by using graphic elements. So trying to optimize for many variables in a process at once usually doesn't work. You need to concentrate on a single variable for a while so you can understand how the changes that you will make will affect the process or the system as a whole. So you want to pick the most important one and focus your efforts accordingly. Throughput means you increase the productivity of the system by changing the system's structure. Essentially, you're tweaking existing resources or you're adding new resources to the system. Unintended consequences, they can change the system, can either be good or bad. However, most of the time, we know that they are bad. One of the major glitches of the Obama healthcare website was unintentional, caused by the changes they made at the very last minute prior to launch. The system was designed that people could browse the exchange, the website, without providing personal information. 2 weeks prior to launching, the administration made a change and said, well, wait, we want people to actually input their personal information prior to them browsing, which caused a lot of problems, a lot of crashes. People were complaining that the website froze, and the system was just completely unstable. A couple of reasons why we'll see that later is that they didn't test it for the scale of the millions of people using that service at the same time. But the key point of this is that they changed the process prior to launch, and which caused unintended consequences. We're going to also see this too in the Cautionary Tales podcast, where in an attempt to prevent problems from occurring, they actually made things worse. Friction is any force or process that removes energy from a system. When friction is present, it's necessary to continue to add energy to a system or process to keep it moving at the same rate over time. Unless additional energy is added, friction will slow the system down until it comes to a stop. If you remove the friction, you'll increase the system's efficiency. Every system has some type of friction. The key is to identify areas where friction currently exists. Then experiment with small improvements that will reduce the amount of friction in the system. If you remove small amounts of friction consistently over time, you can accumulate large improvements in both quality and efficiency. Intentional friction is friction that encourages. It's an example. So you want to slow the system down intentionally, which is sometimes a good thing. The system's going too fast. You actually need to have a slow down. It's like you're watching the tennis, open right now. So they have to, they have a water break or something like that. Sometimes it's good to slow the system down in order to things to catch up. It's not a bad thing sometimes to have unintentional friction. Automation is a great way to improve systems because the greatest cause of problems is humans. Right? Highly automated systems, however, they take quite a bit of people to manage. And so what we have here is we have a paradox of automation. The more we rely on a highly efficient automated system, the more crucial the contribution of human operators to that system. And the irony of automation is that the more reliable the system, the less the human operators have to do, so they pay less attention. So just because we add automation, which is a great way to improve, we got to make sure we keep in mind the paradox and the irony that the value of humans, and that sometimes because we expect that system to be so efficient, we don't pay attention to it. Here's an example of a roundabout. If you guys have roundabouts in your town or not, but a roundabout essentially has a roundabout, right, where traffic flows, and then we have enters, these on ramps and off ramps. So how this was originally designed was the yield was designed that the person coming onto the roundabout had the right of way, and then the people in the roundabout had to yield. So obviously you can see this caused tremendous amounts of backup because it stopped the intention of the roundabout, which is to keep cars moving. This was such a bad case, which was like in the 1900s when this was first developed with this particular yield structure, that Americans just got tired of it. It's like, what, we can't do this. This is never going to work. It took the Europeans to fix it. And what they did is that the Europeans changed the yield structure. So the yield now goes to the cars coming on, and then which created the flow of the cars. So the cars can go on, the cars can go off. And by doing so, that changed the flow of traffic by changing just that one existing yield structure on that. I'll go back to that. The Americans were able to incorporate that roundabout into our cities. In Santa Maria, we've got around 13 or 14 of these things, and they work really well. One thing we got to a law we have to consider when we're doing these is that there's a law called Parkinsons Law, which work expands so as to fill the time available for its completion. So we plan on how much time we have, and when the deadline approaches, we start to make these choices, trade-offs, right? So I have 4 hours to study for the 320 quiz. So I know that I won't be able to study for the 331 or the 211 quiz or whatever. So I have to use that time to study for the 320 quiz. So I'll have to make these choices and trade-offs. You have to decide to do what you need to do by the time you're given. And the thing is that if we only have, if we say that we only have 3 hours, then the work will expand to those 3 hours. This all comes into play is when we do these choices and trade-offs, we are managing for quality by choosing to address the critical quality, doing the things that we have to do in order to meet the needs of the customer. Key step when we're managing for quality. All right, so conclusion, we want to get the person who is doing the actual work and get their perspective, find out where all the problems are. We want to use the correct nodes and connectors. We want to map the workflow, warts and all. We want to validate for waste. So we want to look for rework, for delays, for paper, redundancies. And then we want to indicate non-value added by shading nodes. So again, this is the first part of seeing the process in its actual state. You will do this again after we did a change to the process on our ideal state. That is the end of this presentation, and you will now proceed to the lab.